Okay, so now we'll try to cover another topic. We just saw, convex functions, and we just saw convex domains. That when we combine those, we get convex optimization. Okay. Now, what I want to show you is just be. I want to be a little bit more specific, right? I want to be a little bit more specific. How to work with those domains. In fact, the motivation why you need. So what we want to do here is we want to be able to start working with H polytopes, which are convex functions. They would allow us to form domains of our problems. So a lot of our problems domain would look like H polytope. Those are formed by linear inequalities. And the big reason why we like H polytopes is because H polytopes eventually will be represented in this form, which we already saw. The form is A, let me going to write, AX less than or equal to B. That is the form of a H polytope. Okay. And this is a form that we saw in quadratic programming, and that is the form that will be seen in a lot of other contexts. So it's extremely useful. It's extremely useful. Okay, so as we said in the previous section, convex optimization is when we have convex cost and convex domain. Our convex domains would often look like this. And this is H polytope, and we will try to study it right now. Okay. Now, let us see just a few examples of what H polytopes look like. Just a few examples. So, convex polytope can be this 3D figure. It doesn't have to be 2D or anything like that. Like this thing, which looks like a 3D version of a rhombus, is convex, and it is a polytope. Cube, convex, and polytope. Some convex, how do you call it? Yeah, so like just 2D convex polytopes. They can look like that. And we call it, sometimes we call it convex polygon. This polygon, you can theoretically use, like come up with shapes that are not convex, right? For example, like this shape. Remember we saw on the previous slide. Like this shape is not, the interior of this thing is not convex. So, so that's why we always say like convex polytopes or stuff like this to indicate that it is convex. Like if you want to connect lines to create a shape, you can connect them in such a way that it's not going to be convex. Like this, I don't know, maybe I can call it a polygon. But this is a convex polytope, and it is, yeah, those are convex, as their name implies. What is also interesting is that a line segment is also convex. Of course, the whole line is convex. A plane is convex. So all of those are convex. All the faces of convex polytopes are also convex. All those faces are also convex. The edges are convex. Okay. They're also concave at the same time because they're all linear functions. Okay. That is just to give you like some idea. So we want to be able to use these figures in our optimization. So we want to make sure we can make domains that are shaped like that. How do we make those domains? Well, those domains are made by constructing half spaces. Essentially, the way you can construct, let me just show it on 2D triangle. So the way you can construct a triangle in some ways, let me try to draw it. Okay. So the way you can construct a triangle is, for example, by first just okay. Let me just I guess draw it all the way out first. So no, we need coordinates, at least some coordinates to make it understandable. So those are our x1, x2 coordinates. Okay, so we can designate half spaces which we are not going to allow. What do we mean half spaces? We can say, for example, okay, everything above this is not allowed. So like everything here is not allowed. Okay, good. Why not? Then you can say, okay, everything above this one is also not allowed. So everything above this one is also not allowed. And then you can say, okay, everything below this one is also not allowed. So what remains is this very nice triangle shape, right? So what remains is this triangle. So this is a general approach of how to create half spaces. You cut off half spaces. Why half? Because half of the infinite space is cut off each time, and eventually you get your figure. For example, cube, you can imagine you cut one side, get rid of it, like everything to the left of this side, you cut everything to the also to the right, everything to the left of the side there, cut everything on top of this side, cut everything below this side there, cut everything closer to us on this side, cut everything further from us on that side, cut. 6 cuts, we get cube. Okay, here you can totally mention we cut off something like this. Everything here is cut off. Then we do something like here. Everything here is cut off. Right. Something like here. Everything here is cut off. Etc. You understand the idea. So to generate those shapes, we generally cut something off, and the remaining piece is always convex. This is how we do it. Okay. Now let's see details. Let's see details. Okay. All right. Yep. So convex polytopes are convex. Every 2 points can be connected with a line, right? By definition of convexity. They can be bounded or unbounded. That is an interesting idea. What do you mean unbounded polytope? Well, let's say this polytope with 3 edges and its entire interior being like the polytope is not bounded. Like it goes to infinity. It's still a polytope. I mean, you don't have to call it polytope. If you don't like it, you can call it something else. Like in geometry, we have their own like priorities. So it doesn't have to be like that, right? That doesn't have to be your definition of what polytope is. But for our purposes, for convex optimization, this is definitely good enough to be called H polytope. De facto, we will use this terminology. So good enough. We'll call it H polytope. Okay. So it doesn't have to be bounded. In fact, 1/2 space is also, we can call it H polytope. Wouldn't have a single vertex. Okay. Okay. Now let us just construct 1/2 space. We know to familiarize us with what half spaces are. So half space is defined with this kind of formula. This is what half space is. It is AX less than b, that is the definition of a half space. So here, for example, we see that this is not in the half space. The half space is this. So those green parts is like this, all of this. This is what the half space is. What we cut off is this pink part. Okay. Okay. Good. So this is how a half space looks like. Now, how do we construct it though? In order to construct, we need to know something about A and B. We need to be able to choose those two. Now, let us consider very simple half space. Half space that passes through the origin. So origin is this point here. And we want to consider half space that passes through the origin. And the direction of the half space is defined by its normal vector, n. So n is a normal vector. It points where the half space points. You understand the idea of a normal vector for a half space, right? It's rather intuitive, but what I mean is this vector will be orthogonal to this line, which somehow separates the half space from that we cut off from the half space that we kept. Okay, so this boundary line, we can make a normal vector to it. The vector will be orthogonal to it, right? As the word normal implies. So that is the idea. So we know it passes through the origin and it has a normal vector. How do we find all points which lie on this side? How do we find them? Well, we can say that it is all vectors x such that n times x is less than or equal to 0. How do I know? Well, first of all, points here, they are equal to n times x, for them it will be equal to 0. Why? Well, because they are orthogonal to n. So orthogonal vectors dot product is equal to 0. So at least here it is very clear. What we have here are points that are equal, dot product is equal to 0. Now, what about points somewhere here? Well, those points, they are roughly in the same direction as the normal vector. So the dot product will be positive, not 0 because they're not orthogonal. It's going to be positive. How do I know, by the way, that dot product is not going to be 0? Well, it's also, again, easy enough. For any point here, we can write its decomposition as a sum of two vectors. One vector which is collinear with the normal, and another one which would lie on the boundary. So would be, you know, parallel to this boundary that separates the half spaces. We can also always decompose it like that. And this vector here, its dot product with n would be 0 because it's orthogonal. And this vector here, its dot product with n would be equal to the length of that vector, and it will be positive. Okay, so that is the thing. So all vectors on this side, all vectors here, would have a positive dot product. So all vectors here would have a negative dot product, and that is where this definition comes in. Okay, so this is how we can define the half space, and that is why what we need to do is to just say, okay, A is equal to n, and B is equal to 0 to define this half space. So if we want A transpose n less than equal to B to be definition of this half space, A will be equal to n, B equal to 0. That is how we do it. Questions about this one? Okay. No questions. Okay. Now, what if we are d away from the origin? So the distance from the origin to the half space is d. Okay, d. Euclidean distance, I mean. Distance between a set, like this is clearly a set, right? How do you measure a distance from a point to a set? What is the closest element? Distance to the closest element of a set. That is the distance to the set. So d is a distance from this boundary to or the whole half space, I guess, to the origin. Okay, and still have norm and defining the orientation. How do we write it as ax less than b? Well, no, it is again vectors here are all vectors such that x times n is less than or equal to d. Okay, so it is x, right, just dot x n less than or equal to d. That is if n is normal. That is if n is a normal vector, as in the length of n is 1. Where does this come from? Where does this come from? Well, let's look at the points here again. The points here, how do you define them? Well, let's define just one, like this point, for example. Well, it is a sum of two vectors. One vector is this vector. Another one is this vector. Well, we know that this second vector doesn't actually contribute anything. When you do dot product, we'll call, let's say, this point, I don't know, C. So when we do dot product of C with N, it is the same as doing dot product of, what should we call it? C par is N, whereas C par is this guy, this C par. Parallel, par stands for parallel. So it's only this component that actually does anything. Only this component actually does anything. This component is just perpendicular to the M, so in dot product doesn't do anything. So what is the dot product between C parallel and N? Well, if N is unit vector, then clearly this dot product would have to be equal to D, because D is Euclidean distance. That's kind of like how Euclidean distance is defined, right? So, I mean, if it is not clear, we can continue this derivation as like, what is the dot product is a norm of T par, right? Times 1, right? Which would have to be equal, the cosine between them is equal to 0, is equal to 1. So that's the definition of a norm, and that's equal to D because, yeah, because the way we defined it is, you know, this is the closest point to the origin, and norm of C1, C par is definitely D in this case. All right, so this is where this form comes from. This form comes from this discussion, but n doesn't have to be normal. N doesn't have to be normal. N can be any vector. If it is any vector, we have to normalize it. We say n divided by n norm is equal to D. So we get this expression. If n is arbitrary vector, then we get this expression. But this is clunky. So instead we can rewrite it in this way. We can keep n here and put norm of n to the right. And you know, we can do it on all kinds of ways, but let's say A transpose X less than or equal to B. This can be achieved by saying A is equal to N, and let's say B is equal to d times norm of n. I couldn't write it this one. And this would be more general. This would be more general. This one would work when n is equal to norm of n is equal to 1. This is more general. But yeah, so you can see it's still quite easy, right? Nothing too crazy here. Nothing too crazy here. As long as you know what n is. Questions? All right. Now, if we have multiple half spaces, which is our goal, then what we have is like multiple n1, n2, n3. We get a1, a2, a3, b1, b2, b3 from those, and we stack them this way. By stacking them this way, what we get is just a kind of like nice stack of inequalities, which have to be fulfilled simultaneously. So those inequalities have to be fulfilled simultaneously. That's what we have. And the result is this interior space. So this is what we get from this stacking. Okay, so this is actually very good. And so the result allows us to write convex polytope as this ax less equal to b. That's what we wanted. And this can represent an empty set. If, for example, if we write it something like, let's say, x less than or equal to 4 and minus x less than or equal to, I don't know, minus 7, then this represents an empty set because there is no such x. You couldn't find x that satisfies both of them. Okay, this last one is equal to x bigger than 7, so clearly impossible to find. So it can be empty set, but and this will be kind of like trying to cut off. This is kind of like trying to cut off everything on the left of one inequality. Let's say you cut off everything yellow, right? And then you try to cut off everything on the right of this inequality. You cut off everything red, and what you notice, you cut off everything. There is nothing that you left. So empty set. That is quite possible. And so this one is represents a convex polytope. This is called H representation. So half space representation. H stands for half space. So when you represent your polytopes through inequalities, that is called half space representation. Very useful. And I would suggest you try to use it on your own a little bit. Just try to like write a cube in H representation or a triangle in H representation. It will actually be a good exercise. H representations is not everything that there is. You can also do it with V representation. Okay, you can do it with V representation too. What is V representation? That is vertex representation, where instead of enumerating inequalities of half spaces that you cut off, you just list all the vertices. For example, this one represents a square. What do you mean by that? Well, I'm sorry if we are running out of time. I'll try to be quick. So this represents something like this. Let's say we have our axis. Okay. This is -1, -1. Right, the first point. Okay. -1, -1. Then the second point is -1, 1. What's this one? Next is 1, 1. Next is 1, -1. So there, and what you're supposed to do after is find the convex hull of them. The convex hull is the all linear combinations of those points. Okay. and that is so the representation of the square. You can also write it as the same square with the H representation. For example, here, this is an H representation. The first equation here, this one, right? It says that x1 is less than 1. So this immediately cuts off all of this, okay? Second equation, this one, it says x2 less than 1. So it immediately cuts off all of this. Next one, this one, it says minus x1 is less than 1. It cuts off all of this, right? All of this. And the last one is, of course, as you probably guessed, this one, it says minus x2 is less than 1. It cuts off all of this. So you can see V representation and H representation, they're quite similar. But H representation usually, not always, but usually corresponds to the faces, where V corresponds to the edges. So in, quite often the number of vertices, quite often the number of vertices would be very different from the number of faces. But you know, which one is more nice to use depends greatly. So usually the problem is that the problem that you want to describe can only work with one of those two representations, and both of them are useful. So both of them are useful, but usually only one can work in any particular problem. So you have to know both, and you should be able to go from one to another. How do you go from one to another? Well, you can, of course, just do geometry and find like normals, etc. Like knowing 2 points, you can always draw a line between them, find a normal using, for example, left null space of the line or cross product. There are many ways. But also you can just do go from H representation to V representation, calling a function. People did this enough to actually develop ways to solve this problem. And this problem is called vertex enumeration when you go from H to V. And it's computationally expensive, but it is implemented. You can find it in Python, in MATLAB. It is, I think, as expensive as sorting, plus, of course, you know, overheads, multiple overheads. And from H to V, sorry, from V to H is also possible. Both algorithms are not convex. You cannot use them inside the convex optimization. You have to use them prior or after your optimization. But yeah, they exist. So if you know vertices, you can always construct H by half spaces. If you know half spaces, you can always construct vertices. So just so you know. That is not even all you can do with polynomials. There are also Z representation and other things, but this is enough for this course. That's enough for this course. All right. Last thing, how much time do we have? Do we have 5 minutes or do we are already out of time? Yeah, we're out of time, right? All right, so in 2 words, you could also use the polytopes to approximate difficult convex shapes. For example, here, I'm trying to approximate something that doesn't even have a name. It is like a stadium shape. It's like a summation of an ellipsoid plus a square, something like this, plus a rectangle. But you can see I approximated by making this nice shape. And the approximation is quite close. Those are popular exercises. This is very popular in practice because often difficult shapes are difficult to find, difficult to describe. But polytopes are doing a very good job at describing almost anything. So in practice, often enough, if you have some shapes that you don't know how to work with, you use polytopes. All right, that are usually in approximations or out approximation. In this case, it is in approximation because the approximation is inside the original one. Out approximation would be outside the original one. And yeah, and they should be as tight as possible, usually. Right. I think that should be it. If you want to exercise, you can try to do those in V and H representations. And that's it. That's it. Thank you for sticking with the class. And sorry, I took a little bit longer. Do you have any questions? If not, we'll see each other on Tuesday. And until then.
Okay, thank you, bro.
Thank you. Bye.